Thank you all for being here once again. So this morning's session was focused more on kind of the nuts and bolts of pest management programs, whether it's lanternfly, insects, or diseases. Today, we're going to do a little bit more. This afternoon is going to be focused a little bit more on the equipment that is used to do those kinds of things. So I'm really glad to have both of our speakers here, Jason Deveau and Lynn Sosnoskie, to talk about some of that. So first is going to be Jason, who will be joining us via Zoom, because apparently Canada is still a prison for OMAFRA employees. So Jason is an application technology specialist, so similar to what Andrew Landers has done in some ways in the past. Jason studied biology and psychology at Mount Allison University, plant cell physiology at York University, and plant cell electrophysiology at the University of Guelph. He is based at the Ontario Crops Research Centre since 2008 and researches and develops practical methods to optimize spray productivity and efficacy and to reduce waste. Jason is the founder and co-author of Air Blast 101, Your Guide to Effective and Efficient Spraying, which he co-founded and co-administers, and you can visit at sprayers101.com. And if you have not seen that book, I highly recommend it. It's got some really good information in there, and I'm sure Jason will be referencing some of the stuff that's in that book. So, little plug for you, Jason, right there. So
thank you.
But it's a really nice resource, and I highly recommend it if you have any kind of air blast sprayer, which most of you do. So, Jason, thank you for joining us from across the river, and
thank
take
you.
It away.
They let me out of my prison just long enough to talk to you guys. I'll start by thanking you for having me. I wish I could have been there in person, but it wasn't to be. So I've been given 30 minutes to tell you everything that's going on in new developments in precision agriculture and vineyards, and then teach you how to adjust your existing sprayers, which is frankly impossible. So I'm going to move very, very quickly here. I'll start by sharing my screen, which I'm hoping someone could just give me an acknowledgement that you're seeing a full screen. I don't hear anything, but we're going to get rolling. Okay, great. Thank you. So advances in precision vineyard spraying. And before you think I'm going to send you to run out and buy a $500,000 robotic sprayer, I'm not. So I'm here to kind of manage your expectations. And I'm going to do it in 3 parts. I'll start with a little context. I love this slide. We are in the early days of some really big changes in spraying. And just to give you a sense of how much is about to change, this was considered a big deal back in the day. This is 5 megabytes of storage in 1956. Just to give you some context, the little data keys, the USB data keys we use, it's no problem at all for them to have 5,000 megabytes of storage on them. So as exciting as today is, I just can't even begin to imagine what we're going to be looking at tomorrow. They thought this was a big deal even, 70 years ago. There we go. So let's start with sensors. Precision ag, let's start with the definition, because it's many things to many people. If you're working with cattle or you're working with corn, it's different from what we'd be working with in vineyards. But specific to spraying, let's say that precision ag is detecting, interpreting, and then responding to some variability. Like a lot of the things that we're courting in ag right now, it's taking data and making decisions with it. And sensors enable us to detect things and then make those decisions. And I'm going to do a bit of a timeline here. Here's the evolution of sensors according to sprayers. We started with none. You were the sensor. Whoever was in the tractor, that's the sensor. And in the good old days, there's your sophisticated air blast system, which you think it was hard on the people. I don't think the horses did too well either. All that to say, like, we've come a long way and we've got a lot further to go. But before you dismiss this as comedy, I would maintain that this really uses a lot of the same principles as the image I just showed. This is the generalist. It is a tank. It's a low profile radial sprayer. This photo was taken in 2018. Maybe some of you use a pull blast, or Rears is similar. And honestly, the principles that this sprayer uses to apply products have been working just great for the longest time. I call it a generalist because it kind of does a bunch of things well, but nothing great. And it sure as heck requires a competent operator to dial it in and get the most efficient and effective application possible. The reason these are still out there is because the darn things live for 30 years. They just won't die. And if it ain't broke, we're not going to fix it. And while, yeah, operators will admit they could be doing better, sprayers are expensive and they know how these work, and they work with any number of different plant architectures and morphologies. So they're comfortable with this. And then along came the ultrasonic sensor, and that gave us a new skill, sectional control. And that happened in the 70s. This was in citrus. Bert Roper, a very clever engineer and citrus grower, saw that he was wasting an awful lot of spray on his mature citrus plantations, which, as you can imagine, are great big trees with gaps between them. And working at his kitchen table with a couple of coworkers and his son, they decided to emulate what a bat does and developed an ultrasonic sensor. And that sensor turned entire sections of boom. In this case, in the early days, it was the entire boom, on and off, depending on whether or not there was a target there. Made good sense. And it saved, in the first few years, a reported 80% of all the spray mix that he was using previously. A few years later, the very first one was sold to Coca-Cola. I'd love to know the story behind that, but I don't. And that's not as ancient as you think either. I took this shot, well, it doesn't seem like that long ago, in 2013, of Gillison's GVF ultrasonic system built onto the back of British Columbia's Turbomist sprayer. And this used, honestly, the same principles. Ultrasonic sensors at the front of the sprayer could detect whether or not there was canopy or not. And by the time the header or the trailing edge of the sprayer lined up, well, either the nozzles came on or they didn't. In this case, you can see that it's running the boom in 3 different sections. You can see the electric shutoffs. So this gave us a bit more precision, and sure, the sensors are a little more sophisticated, but the principle didn't change. Now, there are some issues with section level on-off sensors. They are great at managing waste. And, you know, honestly, when you pick up the shiny brochures that say, get a boom that turns off where there's no canopy, they're going to make big, big claims about pesticide savings. And to some extent, that's true. But the amount that you save depends on the size and shape of the plant you're spraying, and whether or not you've got like a continuous hedge, or you have young or individually planted plants that don't form a trellis. And if you have something that looks like a British smile and is full of gaps, then fewer refills and time saved. It's true. But beware, because you have to be cautious of lead and lag. When you turn your boom on, you kind of want that spray to precede the canopy. You'd like to have it blown in alongside the canopy. You don't want to turn it on immediately as soon as you find canopy. Little gusts of wind and strange things that we can't predict mean that you may miss or underdose the leading edge or the lag. So it's safer to turn it on a bit before and a bit after, and that cuts into your savings. And there are some arguments with tall canopies. I know you're grapes, but I thought I'd be complete with this explanation. People that spray tall canopies recognize that the tops and centers of canopies are the hardest to hit and the hardest to cover. And that's because the spray has a long way to go before it gets there, and a lot of stuff can happen to it on the way. So there are some experts that maintain never turn off the top of your sprayer, even if there is no canopy between the trees, because it takes so long to get the spray up there, it's not worth the savings in pesticide to compromise the coverage. And as I just said, and in your case, you're generally spraying continuous hedge-like rows, certainly at maturity. So you're not going to experience the same savings as, say, a peach orchard. And all these things need to be considered before you start to consider investing in one of these things. The next evolution was LiDAR, and I just lumped that in with fluorescence sensors. Now we've gone from sprayer on all the time to sections coming on and off, to actual individual nozzle control. So we have more resolution. We're capable of hitting smaller targets and really fine-tuning what we're spraying, and not just on and off for each nozzle, but variable flow, a certain degree of on or off. If you have a lot of canopy, you get a lot of spray, and vice versa. And there are some that are beginning to tie this technology into air adjustment, although I've never seen it. In this category, we've got something like Smart Guided Systems Intelligent Sprayer. This was developed by Heping Zhu and his team out of Ohio State. And here it's plugged onto a turbo mist. This LiDAR system is tied to pulse width modulation. You may be familiar with this. This is a little solenoid that interrupts flow intermittently. So instead of using, say, pressure to change your flow over time, we just flicker the nozzle on and off really quickly. If you're driving quickly, for example, your nozzle is on more often. If you're driving slower, your nozzle is pulsing, so less flow comes out. Think of it as a kind of rate controller. But when you tie it to the LiDAR system, you can tie the density and the amount of canopy to how long that nozzle is on. Long story short, fingerprint spraying that matches how much canopy there is there to spray. I snapped this shot in 2021 at the orchard right next to my offices. Now, some caveats about this one. Much better resolution. You know, we're not talking feet anymore. This thing can dial down to 10 centimeters, and that does mean a better fit between spray and canopy. But many of these systems make a false assumption, to my way of thinking, and that is the only factor that a sprayer needs to change based on canopy density and size is the amount of liquid it sprays. And I don't believe that's true. These sprayers don't account for environmental conditions. Take, for example, wind. Let's say you're spraying in a crosswind. Your sprayer determines how much canopy is there and says, okay, 50% canopy, 50% spray. But it's blowing hard on one side. So you end up spraying 3 downwind rows on one side, and maybe you don't arrive at the upwind side. Your sensor doesn't know how much wind there is. It doesn't account for the air adjustments on your sprayer itself. If you decide to drop the pedal and speed up, sure, your sprayer will compensate with liquid flow, but now you've changed how the air handling works. The faster you drive, the less opportunity air has to penetrate a canopy or even reach it. So depending on your travel speed and how much air you're using, yes, you might have released the right amount of spray, but we don't know if it actually got there. Air is what moves spray to and into a canopy. And while, yes, these sensors can detect the distance to a target, I don't believe, and I've asked for clarification on this and haven't got it, but I don't believe the sprayer compensates for the distance the spray has to go. What am I talking about? If you release a bunch of fine droplets into the air and it's a hot and dry day, the transfer efficiency, frankly, stinks. They're going to evaporate before they get there. If your target is far, far away, that's a lot more opportunity for spray to blow off target or evaporate into dust before it arrives. The sprayer won't compensate for how far away the target is. And on something like a radial sprayer, like the pull blast that I showed, the top nozzles have to spray a further distance than the bottom nozzles. Each of those nozzles has a different job to do, and the sprayer doesn't know that. And what about the actual flow rate itself? If you buy one of these Smart Apply systems, they come standard 1.2 ounces per cubic foot of canopy detected. And that's great. And I know Heping and his team worked a long time to come up with that number. But is that right? How does your sprayer know if it's spraying a contact fungicide, or maybe an insecticide that's got some translocative properties to it, or I don't know, maybe you're spraying copper. Point is, the amount of liquid you spray and the coverage that's required to get an efficacious application, that's not a constant. And, well, your sprayer doesn't know what that constant is. So the owner is still required to kind of dial in how much flow per canopy for their unique circumstance. And finally, these are smart sprayers. They're going to save a lot of wasted spray. Don't think I'm throwing them under the bus. But there's no way for you to predict how much spray you're going to need, not without a few years experience anyway. You'll drive off with this thing turning on and off on your first application, and you'll probably spray a lot less than you realized. But you mixed a whole tank because no one likes to run out. So what do you do with the leftovers? You paid for them, but now you've got a lot of spray mix to deal with. And as the season progresses and the crop grows and fills in, you're going to end up putting more and more per acre and not still know how much you're going to need. So there's a couple years experience required with a certain cropping system and a sprayer to figure out overbatching and what to do with leftovers. This is still the way the technology is going, by the way, and I believe wholeheartedly we need to get there. But I think we're missing something. I think the pitcher needs a catcher. This thing is, well, it's funny to say it's blindly spraying. It's got eyes all over it, but it is blindly spraying based on how much canopy it detects. The fix would be using optics to identify the target, and then the nozzle flow would respond, and then a digital sensor in the canopy could detect and report deposition. You pitched this much liquid, I caught this much. Is this enough? And then the sprayer uses machine logic to make a decision. Nope, that's not enough to control pest X. So I have to make an iterative change in real time and spray more than I thought I did until I get the coverage I'm looking for. And I picture these things festooned throughout the vineyard. Every now and again, the sprayer is going to pass one and just do a quick gut check to see if it's doing what it thinks it's doing. And I've heard of these things before. There are a couple of researchers that hold patents on trying to build these sensors. I've talked to them in Australia, New Zealand, California, and frankly, we're not there yet, but people are working on it. And that brings us to machine vision. I did say that the machine could make a decision based on what it sees. Now we're talking about machine learning. And machine vision isn't just detecting something that is in your way, like a bat bouncing sonar. These are cameras. They can identify objects. They can determine if it's a weed or the ground. Lynn will talk about that. If it's a bloom or a leaf. And once you have that, you really open things up. We can talk about precision mapping, prescription spraying, and I did mention machine learning. I had the opportunity to go to Australia and see the clever birds at Swarm Farm. If you haven't heard of it, their concept is a series of autonomous platforms that you can put different farming implements on. Maybe they're weeders, maybe they're seeders, maybe they're sprayers, maybe they're harvesters. In this case, they were running experiments in apple where they were trying to detect how much bloom was in what position on these apple trees in an effort to prescription apply thinner and do some crop loading work without sending somebody out there to prune and hedge by hand. So this was the sensor. It traveled along and mapped out the orchard, and then later the sprayer would come along and spray it. So it's not even an assumption you should make that your sensors are riding on the tractor with the sprayer in the back. It could be two separate vehicles. What they end up with is a series of pictures that have to be analyzed. And at the time, analyzing all these images was what was taking all the time. By the time they figured out where the bloom was, you had apples. So it wasn't terribly timely, but we've gotten a lot faster in how we process images. And the kind of things that these sensor/responsive sprayers can do and will do shortly is target identification. Maybe you just want to spray grapes, not the leaves. Well, this thing can figure out what's a grape and what's a leaf and respond accordingly. Maybe, and I've seen this in a lot of field crop talks, we can identify the pest itself. Uh-oh, I know that bug, and I want to just spray that bug. Or even identify damage from an insect. That gives us things like spot spraying. And we're already doing things like that with nutrient management. Then, as I mentioned here, there's bloom detection. Not only how many blossoms, but perhaps even what density of blossoms there are. And the sprayer releases a certain amount of plant growth modifier in response. And that's autonomous crop load management. And vigor. We go along and we look at NDVI or some other indicator of plant health, and that tells us that we're nutrient deficient in certain places. So we don't waste expensive fertilizer all over the place. We just drop it where it needs to go. And the coolest part about these sensors isn't just the spraying, but the fact that every time you drive your vineyard, these mounted sensors can passively collect validation data, which is to say through the season, you can see how your crop changes. You can determine crop load, maybe tie that to harvest. And at the end of the year, figure out, did my crop protection program pay off? Did I get higher quality fruit or higher volumes of fruit as a result of my efforts? Did it work? Because we can only make decisions when we have data. This will give it to us. Whew, we're moving quick. Autonomy. Here in Ontario, like everywhere, boy, it suddenly seems like robots are everywhere. This is just a cross-section of automated ag robotics that are being trialed here in Ontario. Most of them are like what I just said. There are platforms that are autonomous and you just strap an implement to it. Some will take 2 or 3, some will take a lot. Some fly, some crawl, some drag. And all of them are trying to dial in what they do and make themselves worthy of the cost and the effort it takes to run them through the field. They're all pretty specific right now, and they're not without their problems, but we're moving. As we move into autonomy, and I've seen this in a bunch of talks, and I stole from all of them. I think the right way to say is I synthesized something from them. I came up with this path to operational efficiencies and autonomy. The early days, or where a lot of us are right now, is number 1, machine level automation. That means you need a driver. Maybe you've got a rate control system. Maybe you have a sensor-based sectional control system. We'll call that entry level. Task level automation is when the machine itself can start to do some things on its own. You still need a driver, but you've got GPS or RTK positioning. Maybe you can produce as applied mapping. Maybe there's someone monitoring multiple sprayers and can see what went where for traceability. Maybe these machines can synchronize versus Internet of Things connectivity. I'm here, you're there. This is what we need to do to get the job done. And by this point, I'd like to think we're at individual nozzle control. By the time we get to environment level automation, now it's more like driver assisted. Think of a field sprayer with auto steer. This time, I'd like to think there's environmental responsivity, not just say changes in travel speed and rate, but I can detect wind, I can detect temperature, and I can do things about them. I can use prescription applications, not just broadcast. And maybe there's collateral data acquisition. That's the validation data. While I'm driving, I'm learning. Unfortunately, we're not at 3, by the way, just to give you a sense. That means 4 is pretty much out of reach at the moment, but it's coming. Mission level automation, this is operator supervised. Maybe you're not in the equipment, but you got to be there watching, holding a joystick. This might require auto tender systems to fill the sprayers or fuel them, because you start to lose labor if there's somebody hanging around to monitor these all the time. They're self-driving, we've got those. Maybe they can travel with novel traffic patterns. They don't have to go down every row. Drones don't, they can fly over top. And we begin to lose generalist labor and gain specialist labor. This is not somebody with a grease gun that's running this equipment, although don't get me wrong, I couldn't engineer a piece of equipment, so I shouldn't point fun, but now we have people that they're electricians, they are machining experts and robotics experts. And ultimately, operation level autonomy. This is the fleet of robots that do what they do. It's a coordinated fleet, perhaps 24-hour operation, depending on conditions. And the neat bit is self-diagnosis. I've fallen and I can't get up, they yell. Well, I'm going to need a little more than that before I race out and save you. The fact that the equipment is able to figure out what it's doing, where it's doing it, how well it's doing while it's doing it, that's so far beyond us right now, but it is, we'll say, on the horizon. Now, I mentioned we do have some autonomous equipment. We do. This is the first commercially available self-driving sprayer. You might recognize it. The global
Jason?
unmanned. Yes?
Jason, sorry, your slides seem to be stuck on our end, at least.
Where are you? Where did I leave you?
You're still on machine level automation and blank below that on your previous slide, I think.
Weird. Your screen sharing is paused.
All
All right. Let's resume.
Somebody didn't like what you were
sharing.
saying.
I
Apparently.
guess not. Probably someone selling Gus. Can you see it now?
Yes.
Hey, okay. Well, I'll rewind a bit. Sorry, Lynn, I just gobbled up 2 of your minutes. There's operation level autonomy. And this is the Terminator just doing his thing. There's Gus. Pretty, huh? Not too smart, though. This sprayer was the first to come out, which makes it pretty special. It was out of California, and what it did is not hit things when it drove. And again, I'm being a bit tongue-in-cheek. It really was quite an achievement. But ultimately, it is just an autonomous air blast sprayer. In recent iterations, though, there's a smaller version which would fit down alleys for grapes. And it has ultrasonic sensors similar to Smart Apply, eerily similar actually. And it can do canopy adapted spraying, that is individual nozzle control and releasing a shade of gray volume instead of just on and off. And this is a viable commercially available product. Like they're all over the place right now, and their market share is slowly climbing. If we look afar, and I think this is a neat sprayer, I'm so enamored with the shiny brochure on this one. This is the Jacto Arbos 400J AV. The shot's 2021. What's neat about this, yes, it's an autonomous platform. Yes, it's a sprayer. Yes, it responds to canopy with flow, but apparently it can modulate its air too in relation to the canopy. So for example, this really dense canopy will need a good hard blow of turbulent air to get to the center. Then again, the nozzles in the air outlets match the profile of the canopy, so the distance to target isn't quite as large as it would be for a conventional sprayer. So I don't know how they balance one against the other, and I don't know how they determine if they actually got the spray into the center of the canopy, but apparently it can do it, and it's commercially available as well. And then this beast, which I suspect will eat the next 2 years of my life. I took this picture maybe a month ago. This is Provide Agro's, they're the distributor. This is the AgBot. What we have is a Dutch sprayer, the header that's on the back, with Weed It technology. Woo, went too fast. And the Weed It technology is a fluorescence sensor that detects chlorophyll. So this thing goes on and off and uses pulse width modulation to do it, but it's strapped onto an autonomous robot. That's the AgZeed droid at the bottom, three-wheeler, with a big old tank on it. And the long and short of it is, there's your newest version of the autonomous air blast sprayer. And this thing does an extra trick. At the top right, that green funnel is an autofill system. Provide Agro still hasn't been able to tell me how it works. Nobody has, but I guess we're going to find out, because we've got 3 of these things in Ontario this summer, and I'll pretty much be camped out at this orchard for the whole season. We are going to track everything we can about how well this sprayer works, whether it's a time suck or whether it actually saves some, how it fills, the whole 9 yards, and even simple things like how much actual physical manipulation is required on the part of the operator, and how much can it truly do on its own. And I had to take a picture of the joystick because I fight with my 12-year-old boy constantly about the time he wastes on PlayStation, and yet it looks like he's been training for the future this whole time. So he's pretty psyched to drop an "I told you so, Dad" on me. If you're not in the know, that joystick, it looks just like an Xbox or a PlayStation joystick. And I had to laugh when I saw it. I had to eat a little crow. Just to stuff this in, why are we even talking about driving at all? Precision and autonomy in spraying doesn't necessarily have to be restricted to the ground. And Ken Giles knew that a long time ago when he started working with the Yamaha R-Max. I think he was one of the first to get a research allowance for spraying through using a helicopter, an unmanned helicopter in grapes. And he broke all the ground on this. It was really cool work. And he was one of the first to look at the opportunities and limitations. I haven't given you the context you need here or the perspective, but that's not a little drone. That's as big as a motorcycle. It is a big, big vehicle. Unlike this little guy, this is, what is that? I thought that was the Agris. It isn't. That's a Helio out of Texas. And it's what all our growers are clamoring for right now. They all want to spray by drone. If you're not aware, in Canada, it's currently illegal. There are no registered pesticides for application by drone. In the US, it's permitted and hit or miss state by state, but it's an absolute no-fly zone, pun intended, here in Canada. And there are a lot of potential advantages to this system. The timing is super flexible. You don't have to worry about getting in the way of anything, save hydro lines. It's a pretty minimal investment compared to a full-size sprayer. No compaction, no trample. They're a friggin' hoot to use. I list that there because it is a lot of the reasons that growers want to try them. They're fun, but boy, they're slow. They don't really cover a lot of ground very quickly. They can only carry, if you're lucky, 5 gallons per acre. Your spray quality is limited. As I mentioned, at least in Canada, there are no registered liquid products. And, to get right to the point of it, we don't know how to use them. And if someone tells you that they have experience with a drone that sprays, you do have companies down there that have a few years of experience, and they may have very particular usage patterns that they're experienced with. I know how to spray canola spot spray at this stage of development with these nozzles in this drone. It really is case by case because of the very fundamental lack of understanding of how these work. And honestly, this is more in your purview than it is a field operator, because these are flying air blast sprayers. No matter how fast they fly, unlike a helicopter, there's always a downwash. And because of that downwash and how it affects spray fate, it can do some pretty wacky and unpredictable things. When we started playing with them, one of the very first things we did was fill it up with dye and go spray around in volunteer canola in the middle of the night, just to see how much drift we got at different altitudes and different travel speeds. And it was stunning. Like we flew this thing, sorry to mix units, but we flew it 2 meters off the ground and found easily 50 feet of downwind deposition and 15 feet of upwind deposition. And when you're only spraying 3 gallons per acre, that means it's spread pretty thin on the ground. But it was there. And we were starting to learn about how difficult it was to keep the spray on target and how inconsistent that targeting was. We upped our game and moved on to swath analysis. This is a little different than most aerial systems would use. This was developed by a researcher in the States. It's called the swath gobbler, which I just love. And we spray blue dye, the same food dye used in blue M&Ms, over receipt paper. And then that's rolled up under a camera, taking rapid photos until we can build a histogram of swath coverage. This isn't like a field sprayer where the boom's 120 feet, so you get 120 feet of coverage. Depending on your altitude and your nozzles and the wind and a number of other factors, it's not consistent coverage under the sprayer. It may all deflect downwind. And just to go for the trifecta, we did fly a lot of, we'll call them conventional coverage swath testing. This is based on Project Safe, which is what we use for aerial fly-ins. And water sensitive paper was laid out under the swath, and we tried to figure out where the spray went. And what we learned was that the swath is incredibly narrow. It's not a big flat bell curve or a trapezoid. In fact, it's got a really sharp peak in the middle where you over apply directly under the drone and quickly dwindle to not enough to either side. So when we start slapping these curves on top of each other and you add up the repeated coverage under the curve, we found it was really tricky to flatten this overlap out. Ultimately, we were pretty comfortable saying that flying a 4-rotor drone 2 meters above the ground or the crop or whatever your target is will give you a 3 to 3.5 meter effective swath that is fairly consistent coverage, which for grape might be good because narrow rows. But before you get too excited about a drone's ability to blast down through a canopy, I just want to show you this. This is coverage through relative indexing. Lots of big words, but it really will make sense. Just imagine you've got an air blast sprayer in some canopy. Could be a grape, could be a Christmas tree, it doesn't matter. Let's say that the amount of spray we get up here, we'll call that 1x. We'll say that's our goal. That's the target amount of coverage. Well, because of the proximity to the sprayer and how little distance there is and how much air energy is focused on that spot, and this is, by the way, any crop, this is just physics. You could expect to get 3 times as much in that position. And way here on the other side of the canopy, far, far away from it, you'd be lucky to get 1/10 of what you got in the top right. And this should make some sense because the canopy itself is a great big filter. It gobbles up any loose spray, it burns out air energy. It's really hard to spray to the other side of a canopy. As I keep telling people in nurseries who ask me why this doesn't work. Hey, can you help us get good coverage? Well, what are you trying to do? Well, we grow cedar trees. We use them for drift barriers. You do? Well, what are you trying to do? Well, we'd like to spray through 5 of them. We seem to be having a hard time doing that consistently. We get too much next to the sprayer, not enough 5 trees away. Wait a minute. Aren't you growing these as barriers to spray drift? Yeah. And then you wait and you hope they put 2 and 2 together, but quite often they don't. But the point of this is the further away you get from your target and the more canopy in the middle, the less coverage you can expect. So flying a drone over a canopy means it's going to have to drill from the top down. And there are guys out there working, spraying over alleys and trying to find the best fit to get good coverage, but you'll never get around this problem of physics. That's why we have sprayers that spray multiple rows. In talking about precision ag, it doesn't necessarily have to be sensors and computers and brains. It can be something as simple as understanding how spray moves. Here we've got 4 examples of over-the-row systems. I say 4, even though I've got 5 pictures, because I don't like the one in the top left. That's designed to spray 3 rows, sure, but it does it by trying to spray down from the top onto the adjacent rows. And quite often what happens is you get a ton of drift from the outside rows, or if you try to back the drift off, you don't get sufficient coverage. Some nozzles are very close to your target, some are just too far away. I much prefer the ones that keep the nozzles in the air equidistant from the target. Bit of a commercial. Okay, home stretch, everybody. Air handling is the most important and least understood system on a sprayer, and I'm telling you that you're still going to need to do manual adjustments no matter how so-called intelligent your sprayer is. This is the goal. We want to push all the spray out of a empty air out of a canopy and replace it with spray-laden air. Now, believe it or not, the one at the bottom is kind of what we're trying to do. We drive down one row, we shove it halfway in. Hopefully none of it escapes out the back end, and then we do it on the other side. If you're driving every second row, which I wish you wouldn't do, then you're trying to do what the very top shows. If you're blowing way too hard, which is quite often the case, you're doing what you see in the middle. You're not getting great coverage next to the sprayer, and you're blowing it all out the back end. So I'm going to give you a few steps, no matter how sophisticated your sprayer is, to help you succeed or maybe do a little better this year. Number 1, check your sprayer out before you use it. Sure, you put it away in a certain condition, but mice like to build nests in it. Things like to crack off the inside of tanks. Things flake out of the inside. It's just not going to be the same beast you put away. So make sure you check it out before you use it, and do a visual walk around each day before you spray, maybe while it's filling. I like to use a checklist to keep myself honest, a 5 or 10 or 15 point checklist looking for cracks and rub points and wear, looking for anything that may be leaking will save you a lot of heartache and pain halfway through your spray day. And I mean, things can happen so quickly. A buddy of mine is an aerial applicator. They went for a nice government lunch, 2 hours. And when they came back, some bird had made a big nest in the engine of their plane. So check your sprayer out. You never know what you're going to find. Step 2, this is where the air becomes so important. Park your sprayer in an alley between 2 rows, tie some pretty ribbons on the outside along each air outlet, and then turn on the air. Watch the way the ribbons straighten out. This allows you to extrapolate where the air is aimed. This is how you adjust deflectors. This is how you determine how much air energy is blowing over and through, over the top, into the ground, into the great blue. It's just a waste. We don't need it. You can see in this particular image, there are 2 deflectors at the bottom of the sprayer. The one on the left is canted down. The one on the right is canted up. And if you look at the ribbons, the white dotted lines are symmetrical, and yet you can see how the ribbons are skewed based on how the deflector is set. These deflectors do a really, really important thing. And if you don't have them, you should. Also, these are almost decorative. They're way too small. I'm a big fan of at least extending the top ones. The bottom ones, you can't go too much further because they stick out beyond the tires. But imagine putting 2 big flat deflectors on the top, you'd be able to focus all that air energy into a canopy. Next step is to tie a ribbon onto a stick, slap on your safety glasses because air blast sprayers blow everything, and feel your way around the air. Just because the air is aimed correctly doesn't mean it arrives. You can see in position A, the ribbon lines up. It looks like it's en route to the canopy. But if you were to lift it up a little higher to position B, it goes limp. You don't have enough air energy to reach the target. Maybe in position C, there's a gap in your air that you can't see. Well, with ribbons, you can. Or if you hold it down where D is, you see you're blowing into the ground. A little explore with a ribbon on a stick can teach you a great deal. Step 3, Adjust the air direction to just overshoot the top of the grapes, and don't worry too much about the bottom. As long as you're not blasting into the ground, gravity will work for you. Secondary deposition will always cause spray to settle into the lower canopy, at least on the upward facing surfaces. So a lot of our focus should be at the top of the canopy. You want to just overshoot it. And I say just overshoot it because sprayers rock, particularly towers. And since the tops of canopies are notoriously hard to hit, we don't want to dip down and miss the top of a canopy on uneven surfaces. Instead, it's better to hedge your bets a little bit and go a bit higher. The possible miss at the bottom of the canopy, gravity will generally take care of that. Step 4, more ribbons. This time, tie them on the other side of the upwind panel of grapes. At minimum, put them at the top of the canopy, but certainly put them along what you think to be the densest and widest point. And then with your tank half full of water, start driving by. You're going to have somebody watching on the far side. And if you see those ribbons not moving at all, in grape, that's probably a bad thing. You want them to wobble just a little bit. That means you're using enough air energy to arrive at the target and penetrate that target and carry the spray with it. It's inevitable that some's going to escape a little bit. If it's just hanging limp, that probably means you're not using enough air. A little's got to escape. If it stands straight out, then you're probably slipstreaming or blowing it straight through the canopy or causing parts of it to collapse and not get even spray deposition. It's noisy, it's a waste of product, it's a waste of energy and fuel. There are some ways you can be tricked. Air deflection may channel through the grape, so be sensible about where you put the ribbons and understand that air, like water, will take the path of least resistance. And the kind of air you're using matters too. If you're using something like a tangential fan, it tends to make laminar air, straight strips of strong moving air. And they have a tendency to kind of mush grape leaves together, to close them like two sides of a book. It's called shingling. And what that does is closes the canopy. The insides of the leaves will kind of protect each other, and it'll force the air to move into channels. Better to have turbulent air, or if you have to have laminar air, aim it at an angle to sort of flip the leaves like a spatula in a fried egg. Always angle them a little ahead or a little behind. If you're using a multi-row sprayer, you never want to do what you see in A. Air smashing directly into air, bad news. It's just going to bounce all over the place and cancel itself out. B and C, that's great. Any angles at all so that they're not directly at one another will improve coverage. If you're using multiple fans, it's a little different because they tend to be more turbulent. It's not such a big deal if they're aimed directly at each other, but small adjustments in their angle are best. I would avoid F because it tends to roll away. And canopy management matters. Stripping leaves, getting things out of the way. If you can't see what you're spraying, your spray probably can't get there. One of my colleagues in New Zealand, I love it. He says, if you're in an apple orchard and you can't see if the person on the other side is naked, you have too dense a canopy. Now, I don't know how many guys are running around bare butt in Australia, but it's hot and full of flies and I wouldn't recommend it. But if that's their metric for pruning, so be it. Step 5, fan speed. If you're overblowing, if that ribbon stands straight out, you have choices. You can drive faster, you can lower the fan gear, you can do a lot of different things. Gear up and throttle down if you have enough horsepower and you're not on rolling ground. And it's neat to see what happens when you speed up or slow down. The slower you travel, the higher your spray will go and the deeper into the canopy. You see that on the left. The faster you drive, the less opportunity your spray air has to arrive at its target. So it tends to bend back. It doesn't penetrate as deeply and it doesn't go as high. So if you've reached the edge of what you can do with sprayer settings and you're still overblowing or underblowing, your travel speed is a wonderful tool for doing it. And it's why in this process, I always adjust the air first, long before I get to the nozzles. I think I just said all that. And finally, we start adjusting flow in each nozzle position. Each nozzle has a different job to do and a different portion of canopy to cover. So using some sort of coverage indicator, usually water sensitive paper. If you see too much in one position, back it off. If you don't see enough, bring it up. And I wish there was an easy way to tell you how to do this. In grape, fortunately, you can use the same rate up and down the sprayer outlet without worrying about it too much. In trees, it's a different story, but it is an iterative process. My recommendation is to take half a day, some water-sensitive paper, and fiddle around until you like what you see. Water-sensitive paper is dirt cheap compared to the benefits it's going to give you. And this kind of looks like close-up magic, but there are ways to handle it quickly and easily. In this case, I should be wearing gloves, but I've been doing this a long time and I'm kind of cavalier. But you pull a bundle out, you wrap one around the top, only the yellow side is sensitive to water, and you fold them over by pinching it like a sandwich. And then feeding them out one after the other, you can drive a pin through the corner and you just drop them all into a Ziploc bag and you pin them into branches, leaves, the trunk itself, the vine, even into the trellis, wherever you want, and drive by and spray. Now you've got two sensitive sides and they're all over the place. As for how much is enough, that's a whole other talk. But generally speaking, 85 drops per square centimeter and 10 to 15% overall coverage should be sufficient for even the most brutal contact fungicide. If you can do that on 80% of your papers, then you're laughing. You can see from the water-sensitive papers above, it does tend to get a little complicated, but don't lose track of what you're trying to achieve. If it's a mobile insect and it's something that's going to bait them to eat it, well, you don't have to be quite so diligent. If it's a contact fungicide or a spotted wing Drosophila deep in the canopy, you may want you may want a higher droplet density, but that's a talk for another time. We're almost done. Recognize that water-sensitive paper is not a leaf. It is not a grape. It will spread differently. In fact, it won't show the use of adjuvants. Unlike stickers and spreaders on a leaf or a grape, they just don't spread the same way on water-sensitive paper. So we only ever compare water-sensitive paper to water-sensitive paper, not to actual plant structures. And it's actually far easier to land spray on the leaves than it is on the grapes, 4 to 10 times harder to get spray to stick to a grape. So depending on the job you're trying to do, recognize that changes in spray quality and the air handling may be required to achieve them. Yeah, like I said, if you get too much, you're using too much. Don't freak if you drench the outside of your panel just to get a few drops to the inside. Because of that relative indexing I showed earlier, the spray has to get through the outside to get to the inside. So that's kind of the cost of doing business in some cases. But in an attempt to be efficient, pruning and hedging and better air handling tend to even out deposition a bit. And recognize that as the canopy grows and fills, you may have to change what you do. Now, this is hops. It's a pretty extreme example, but it is an example of how canopy changes throughout the season may warrant changes to the sprayer. It's been my experience that a little excessive coverage early in the season when fungicide applications are absolutely critical isn't such a bad thing. It sort of self-corrects as the plant grows and fills. But at some point, you may need to, I don't know, alter your air handling by slowing down a bit. That has the added benefit of increasing your flow because you're there longer if you're not using a rate controller, and that'll compensate for changes in coverage. But the point of this is simply to be aware that what you started spraying in the spring is not the same beastie you're spraying pre-harvest. And just to let you know, we'll go full circle. Even though these are all manual changes, there are sprayers out there that take advantage of precision and technology and allow you to make these changes. I never know if it's Fade or Fide, but this is out of the Spain area. This is the Future H30 Smart Tomizer. Boy, they come up with great names. What's neat about this is it regulates dose, just like sensors do, but it doesn't use sensors to do it. It uses tree row volume. You have to plug in a bunch of metrics about your crop, and it decides how much to spray based on a model. Likewise, the propellers on the back of this have variable pitch. That means it'll make more or less air. Again, based on a formula where you plug things in and it decides how hard to blow. So I'll give it the credit of making these changes much, much easier for the operator. But you'll note that it still needs your brain to operate. And so we'll end with this. You guys are still employed. Anyone running your sprayers right now, treat them like solid gold. The more years they have behind them, the more wonderful experience they have to bring to the program. Every single sprayer you've seen here, from the one on the back of the horse to the most sophisticated Gus, still require human judgment. You are still required to optimize air direction and air energy in relation to your canopy size, the speed that you're traveling, and whatever environmental conditions you're spraying in.
Hey,
Please
Jason?
use, yep,
We need you to wrap up.
this is my last one.
Excellent.
Please use water-sensitive paper or some other means to quantify coverage so you know if you're getting the coverage you think you're getting. And finally, adjust your practices throughout the season. Pick up the book we mentioned, go to the website. Whew. Okay, I'll draw a breath.
Thank you very much, Jason. We appreciate it. Just in the interest of time, we're going to move ahead with Lynn's talk. But as I said, that Sprayer 101 resource is really terrific. And a lot of what Jason talked about today is in that. So please, I recommend it again. So our next speaker is Lynn Sosnoskie, and I'll give about 5 minutes of introduction so that Lynn is our, Lynn, that's right, exactly.
I think it was about 10 minutes.
Lynn is our weed scientist at AgriTech and has been there since 2019. Excellent. And has been doing some work on some novel weed technology stuff. And so I wanted to have her come and talk a little bit about that.
Yeah. Hi, thanks for having me. I am the weed scientist at Cornell. And just a full disclosure, my crop spectrum that I cover, I am not just exclusive to grapes like Katie, or I'm covering grapes and apples and hops and hemp and Christmas trees and all vegetables in the state of New York. So just understand I'm working in a lot of commodities. So I do dabble a little bit in each, but I do want to talk about some of the work that I'm doing in grapes with respect to novel weed control technology, and also what's on the horizon, what is coming that I think we're going to be able to have here in New York. So we will skip this of why we want to think about weeds in perennial crops and why they're important, except to kind of highlight what I'm sure Brian Eschnauer and Alejandro Calixto have been talking about is, one of the weeds that is causing a problem in our systems, are going to threaten our systems, is going to be this invasive tree species, tree of heaven, as a preferred host for the spotted lanternfly. So we know that herbicides are frequently used tools across all of our commodities across the United States. And that doesn't mean that horticultural crops are excluded. These are some of my herbicide research trials out at the Cornell Research Station. Just to let you know is that I do herbicide evaluation. I'm currently working with ISK Biosciences. This is their product Tifenicil. It's going to go under the trade name Gamma. It's already registered in a few Western states. And then I have been looking at it alone and in combination with some residual herbicides, both for burn down and then extended control. It is like AIM-EC. It's a very similar to AIM-EC, carfentrazone. It's a PPO inhibitor, except it picks up grasses. And that gives it some value, especially if we want to start maybe moving away from products like paraquat that have a lot of restrictions associated with them. It's also a very good product for sucker control. It's as good as AIM-EC. So we've been working out at Cornell. We've supplied the data to the manufacturer to support a registration. We're in preparation of a weed technology article with Oregon State University, who's also evaluating it. And we're also working with BASF to look at a new premix product for grapes. And those trials got started last fall and will get started this spring out at Cornell. But herbicides aren't always desirable. There's a lot of reasons why we not be wanting to use herbicides, whether it's resistance or injury potential to the crop, environmental concerns, worker safety, the cost associated with chemical products, and then changes in consumer preferences and regulatory environment, which I'm going to talk about in a second. We do have herbicide resistance in orchard and vineyard cropping systems. Most of these are from the Western United States out of our almond and our walnut systems. But the leftmost picture, that is horseweed, mare's tail here from New York. And you can see we have 2 that look perfectly fine and 2 that are obviously damaged. The 2 that look perfectly fine, those are paraquat resistant mare's tail. That one that we got out of a vineyard in central New York and one that came out of an apple orchard. So we do have glyphosate resistance in mare's tail, which is widespread, but we now have paraquat resistance that we've confirmed, and my graduate student is preparing her thesis on and for publication. Obviously, environmental concerns, injury concerns. Do get asked a lot of questions about glyphosate injury in grapes and people wanting to give me like, well, exactly how much yield could I lose? How much damage am I going to see? And just to let you know, it doesn't work that way. There's a lot of factors that are going to influence injury from any herbicide, including glyphosate, and it's going to be dependent on the timing that the contact happens, whether it's early season, post bloom, the rate or the dose that's received, if it's a direct spray versus some sort of indirect drift. If you get it onto suckers, the contact area that actually uptakes material, and then vine vigor. Understand that vines that are stressed either in the current season or the previous season are probably going to have a different response than one that's less so. We get asked about, well, when are the new herbicides coming? And just understand, we have plateaued with the number of herbicides that are being released. That's the heyday of the 70s and the 80s, and there was always like a new herbicide, particularly an ALS inhibitor coming out. That's over. It's very expensive. It takes about $200 million to bring a new pesticide to market. That's from discovery to commercialization. So it's a very expensive process. There's a lot of discussion in my own community, the Weed Science Society, about whether we've just there's a limited number of physiological target sites within the cells themselves, and have we maxed out, biologically. And then a lot of discussion about whether the consolidation of chemical companies has helped or hurt the discovery process. We used to have 30 chemical companies or more, and now we're down to like the big 9. All right, then consumer perceptions and regulatory mandates. And I'm just going to mention the EPA and the Endangered Species Act. All federal government agencies need to comply with the Endangered Species Act. When anything they do could damage, threaten an endangered species or an endangered species habitat, okay? And the EPA has been largely non-compliant with their statutory requirements under law to have formal consultation procedures with the Fish and Wildlife Service or the National Marine Fisheries Service. And so they've got a work plan in place to basically become compliant, because courts have indicated that non-compliance is just not an option anymore. So what does this mean? Well, it means that, again, if they think that a herbicide or a pesticide could cause damage to an endangered species, they have to go through a very extensive process to document the potential damage, and then change labels to mitigate that potential impact. But they also have to meet their FIFRA obligation. So the EPA is, bound by ESA, but bound by FIFRA. And FIFRA requires a risk and a benefit balance. So basically what I think is going to happen as new products come onto market is, I think registrations are going to get slower because there's going to be more detailed evaluation of the products and the data behind the products with respect to endangered species. It could lead to rate changes on labels. Say a label goes up for re-registration. It could change the rates. It could change use patterns of products, and it's really going to probably bring in mitigation requirements. So what does that have to do with technology? Well, for me, technology is one of those novel tools for us to either reduce herbicides or eliminate herbicide use. And I think that means for when we do use herbicides, that it is going to preserve some of those chemistries longer. So I want to talk to you about the novel technology out there. And the first I'm going to mention is electric weeding. I mostly get eye rolls and people being very scared about this, but there are several companies that are engaged in electrical weeding systems and the evaluation of electrical weeding systems. So one of them is RootWave. This is a company out of Europe that's using electricity to kill weeds. without the chemical herbicides. Basically, what it does is that you pass an electric current through the weed. The flow of electricity generates heat. The heat causes water in the cells to vaporize. When the water vaporizes, it expands, the cells burst, and then those tissues wilt and die. So again, Root Wave just put out an announcement that their Root Wave Volt is on the market, and they have a limited number of units available. It is only available in Europe. They've not entered the North American market yet. In my emails with them, they don't have any plan to enter the North American market right at this time. I, however, am also doing some work in electrical weeding, and this is from the Zaso company. The Zaso company is out of Brazil. They are operating in Europe, and I believe New Holland has some vested interest in this technology, and they're looking to potentially bring it to North America. Again, what you have is you have a PTO-powered generator on the back of the tractor unit. It supplies electricity to our weeding implements on the front. And basically, those electrodes are just metal, flexible, finger-like fins that they bend. They just brush like a wiper over the surface instead of passing, covering the weeds with a herbicide. It's actually, they're passing an electrical current through the weeds. So this is some of the work. This is an OREI project, a USDA Organic Research Extension Initiative project. It's UC Davis, Cornell, and Oregon State. We are doing it together, and we're doing it in apples, hops, grapes, hazelnuts, almonds, and blueberries. So we got our system last summer up and running. This is us. We were just testing the unit. As it's running, we were doing it in bare ground. We're moving it into crop this spring. My colleague in Oregon State has done it 2 years in blueberries and 2 years in hazelnuts and has in crop data. We went in hops last year as well. So, but basically you can see the area that it was killed by the electric weeder. This is about 2 to 3 weeks after treatment. You can kind of see the delineation of damage, which is the width of the metal fins. And our preliminary data that my PhD student is doing has shown no impacts yet on the number or the diversity of soil microarthropods or soil microbial respiration. Again, this is my Zaso unit. That's a still shot of the Volt from Root Wave. If you're interested in the technology, Google Zaso and Root Wave and electric weeder, and you'll get their videos and you'll go to their websites and you can learn more about the technology. The next I'm going to talk about is a GPS guided autonomous robotic weeder. This is the NIO TED. Jason showed some NIO units in his previous slide. I actually have one of those NIO units. It's a NIO Oz weeder that we're going to be working with this year. This actually goes over the vine row. There's no vision associated with it. It's smart only in that you program an AB line into it and you put in the configuration and you build the map for your vineyard or your system, and it just goes and comes back and goes and comes back. And it has basically large finger weeders, most of them that are at the base, and they're autonomous and move through the vineyard system. So I have seen pictures. NIO was actually on campus yesterday. We were working on updating the programming in my NIO unit. I'm working with Jen, and I'm working with Hans, and I am working with NIO to try and get the TED out to Clarel this summer and to the Geneva area for demos. They showed me some pictures of it on slopes, which I thought was really impressive because that was the first thing I brought up is we've got slope, and they showed me pictures of it both going up the slope and across the slope and the degree that it could work in. It also had very rocky soil. So I was very interested seeing that, knowing how glaciated New York could be. So if you're interested in something like that, you can Google NIO TED. Like I said, we're trying to get it into New York for evaluation and demo this summer, coming out of Ontario. And then I'm going to talk about some targeted herbicide applications that we've been doing. And Jason brought up the Weed It technology. Well, that happens to be the system I have on my sprayer that I'm doing work out in Clairol. So why are we interested in vision-guided spray systems? One, to try and reduce the volume of herbicides that we're applying, reduce the crop injury potential through that could be associated with post-emergence applications. And then could we possibly evaluate a new herbicide? If we can increase the safety factor because we're only targeting the weeds and we're not using as much spray product, could we possibly bring a new herbicide on market because now of the lack of potential movement? So this is the Weed It system. This is mine. It's custom built from the Weed It company. This technology is used out mostly in the Western United States for precision spraying, particularly in fallow systems. The Weed It.
Busted.
Anyway. So anyway, the Weed It has 4 sensors associated with it, with that green box. There's 4 sensors. Each of those 4 sensors control an individual nozzle. And you can see where you on the bottom, you can see the 4 channels. And you can see the blue light from the NIO sprayer. So 1 sensor in each of those channels, and then 1 sprayer nozzle associated with each of those sections. Basically what it is, unlike some of the other technology out there, like the Green Seeker that just sees green on a brown background, the Weed It system actually looks for chlorophyll fluorescence. So it emits a blue light absorbs the chlorophyll. Chlorophyll emits a near infrared wavelength in response to the blue light. That sensor picks it up and it immediately turns on the nozzle to spray the weeds that are within that range of the sensor. So my colleague in New Jersey has done the work in blueberries. I've been doing it at Clairol in grapes. Don't worry about all of that. Just want to show you is that in his study with blueberries, basically he did a banded application and compared it to the Weed It system, whether he was looking at the top of his bed or he was looking at the side of his bed. Basically, regardless of the herbicides he was using, the Weed It was just as effective for controlling weeds as his banded application. He didn't see any difference in either of those systems with respect to weed control. Now, in 2021, he didn't see any difference in injury. In 2022, he did. He got significantly more injury in his Weed It system. And he was like, well, what's going on? And this will go into some adjacent stuff, is making sure you're calibrated and making sure you know where your spray nozzles are. He basically had this ATV died, and he bought this ATV, but the mounting location was 2 inches higher on this ATV. And that suddenly just changed where his spray targets were going. And that's why he saw the injury. We did this at Cornell and the Clairol Research Station. This is my technician, Liz. That's our unit. Basically, the black line, this was Rely 280. We did a bunch of different herbicides. I'm just showing this one because this is our registered herbicide that we tested. The black line is our untreated check. The red line was a traditional banded application. The blue line was our vision sprayer. In 2021, we weren't as good with the vision sprayer as we were with the banded application. We started way too high. Our starting weed density was around 50%. I'd rather be around 20%. That's where we were in 2022. And those lines converged a lot better in 2022. Really, as soon as you start getting densities really high, you don't start seeing use reductions, and basically any of your vision sprayers just turn into a regular sprayer because they're constantly being turned on. We also looked at it for sucker control, looked at a bunch of different herbicides, but basically could our vision sprayer see the suckers on grapes and could we control them? And basically what we saw is that don't worry about the herbicide, the AMEC and the Tifenicil equal not as good as the Rely 280. Lower numbers here are better. because this is biomass per vine as a percent of the untreated check. Basically, the Vision sprayer was just as good if we put a banded, like a directed application to the base. We also reduced herbicide use by 40% using the weed sprayer. We would have been higher, a lot higher, except there was a rye cover crop in the middle between the vine rows, and my inner sensor kept detecting the rye cover crop and kept turning the sprayer on. So this is my last slide, need. So I think there's barriers that are going to, the need for technology. There's barriers that are going to impact herbicide use, weed control, and, technology, I think, is going to be a tool for grower adoption, but I don't think technology is going to be a substitute for a very diversified, well thought out weed management program. Technology obviously requires some sort of capital investment. My weed sprayer was about $15,000. My electric weeder was about $50,000. The TED's probably about $200,000, just so you know. But it's not just the capital investment. You have to factor in the ability to service the units and parts costs. Now, that being said, all of these costs start to come down the more widespread the technology gets and the more players that are in the market. As Jason said, you're not going to get rid of labor. We're going to change labor. Your labor is, you're going to need workers that are going to have very unique and diversified skill sets. They're going to need to know programming. They're going to need to have a mechanical and electrical training, and they're probably going to have to be as good with a wrench and a welder as they are with a computer. So we have to think about whether we're training the next, the next vineyard worker or the next farm worker. Regulatory, this is one thing that the United States, Canada too, we are not prepared to handle new technology coming into the market. For instance, geofencing with autonomous robots, what kind of geofencing is going to have to be in place? In California, autonomous weeding robots are under the exact same rules that autonomous self-driving cars are. That means they have to have an operator with them all the time. Okay. And they got swept up without some sort of cutout for them. So are we thinking ahead from a regulatory standpoint about these tools? Also with the EPA, our labels are not written for a targeted spray application. So we have to think about are the companies and the EPA working together to think about the use of their tools with that technology? There's a lot. We are behind the ball. This technology is coming faster than our regulatory environments are anticipating. And what happens is we're all going to get kind of caught up in the nether region. This isn't going to stand alone. You have to have diversified, integrated practices, and smart technology. It simply is not infallible. Okay, it's smart in one respect, but the operator is still the smartest part of the whole system. And just to acknowledge their funding, and thank you very much.
You pretty much nailed it. If there are a couple of questions, we do have time. I think Jason is still with us. Any questions for either of the speakers? They answered them all.
I don't think I can ship beer to the US, but I'm going to have to send something to Lynn for expediting her talk and making up for my.
Oh, you damn well know it, Jason.
Oh, yeah. Yeah. Yeah, I'm going to eat this.
By the way, Jason actually knows my husband. They went to school at Guelph together, so I feel I'm allowed to say that.
Oh, whether you do or not, I deserve the slap. In retrospect, I should have cut that drone part out.
All right. So thank you all very much, both online and here in the room. Just a quick note again, those of you who are online, we need you to fill out the short little electronic form that should be going. The link should be showing up in the chat right now. So please go ahead and fill that out. And
I just saw a question about the amperage on the Zaso root wave that Paul asked. Yeah, so Paul, that's actually a really good question. The amperage is going to depend on a lot of different factors. It's going to depend obviously on the amount of vegetation that's present. It's also going to depend on the soil type, because different soil types have different resistivity. And the amount of water content in that soil is also going to affect current flow. The other thing is that we've been talking about, we've been measuring amperage with the work that we've been doing. I've been measuring amperage. We really probably need to translate that into joules, because joules is a measure of work as opposed to amperage.
Plus, you'll need rubber boots to not get electrocuted, right, Lynn?
You know, everyone expects to see arcs and sparks and fires. It is actually the most anticlimactic technology out there. It sounds just like it's the motor running and you're like,
Yeah.
okay.
Yeah, it's much ado about nothing. They're pretty neat systems.
It is, there's obviously going to be a lot of safety training. But with the Zaso weeder, I literally just walk up to it and my technician stops. I walk up, I change the dial on the setting for the unit, which is on the generator itself, and then I walk away.
All right. Thank you again, everybody. Those of you who are here in the room, your certificates will be outside if you'd like to pick those up. Again, those of you who are on Zoom, please be sure that you've finished that Qualtrics link. We'll keep the session open for a little while, so you can be sure to do that. And thank you all very much.